I just sent out an email. I don't know where the rest of the people are, but those of you who are here, thank you for showing up. I'd like to apologize, excuse me, once again for Tuesday night, or not Tuesday night, Tuesday. It seemed like a whole night and everything, but anyways, Tuesday, I lost internet service from about 9 till just after noon. Uh, it's about the third time in the last 10 years that's happened to me with WoW. They're quite good, but I tried logging on with my phone and I couldn't. I've changed something so I can, hopefully in the future. And I'm also going to ask COD, some people there, come up with a plan where someone can enter my Blackboard account, because I can't if I don't have internet service, and send out an email to all of you. But I'm here. And Christopher, good morning to you too. All right, let's get going. All right, couple things. First of all, I was going to talk about today how to remove test anxiety. And I'll send this out in an email. Since we missed Tuesday, I'm going to postpone it till next Tuesday. Instead of after class, I'm going to start class 15 minutes early on Tuesday. And if you want, stop by so you can learn about how to eliminate test anxiety, or come at 10 o'clock when we normally start. As I mentioned before, it works real well. I've been teaching this for a number of years now. I will eliminate it from the recording that I put on YouTube. So if you can't make it to our lecture, please see me during my office hours. I'll be more than happy to teach you that then. All right, because we lost Tuesday, I'm going to spend some more extra time today in our Zoom meeting, lecture, and lab. And I'll do the same Tuesday and maybe the following Thursday. If you have to leave at a certain time, feel free to, because I'll be posting this all on YouTube. By the way, thank you for making Dr. White a YouTube star. Not really, but it looks like all of you are being helped by that, which is a good thing. All right, one of the things, since I'm going to be going longer and some of you might leave early, I'm going to do something different today. And that is, I'm going to start with our lab. And don't forget the lab that we talked about last Thursday is due today. By the end of the day, you should upload it. And also don't forget to fill out the home lab sheet, agreement sheet, or safety sheet. You can upload them both in the assignment area for lab 1. I checked with people who did that already, and it worked fine. So remember, lab 1 is due today. If you don't have a printer, just write out your answers for the question, upload them as a PDF file. If you go to Blackboard, let's see, do I still have Blackboard open on me? No, oh, hold on. Everybody should see on their screen Blackboard where it says announcements and stuff. And if you look over here, I now have an area which, if you click on, which it says PDF instructions, it opens it up to 2 files. One is a Word document, the other is PDF if you don't have it. And it teaches you, if you don't have it, and even if you have a scanner, if you don't have a scanner, it shows you how you can use your cell phone to make a PDF file. And my students this summer used it for 4 tests, the final, and 13 labs, and it worked fine for them. If you have any questions, always feel free to ask for help. Remember, in my class, there's no such thing as a dumb question. All right, today we're going to do lab One of the things I didn't stress, my arm isn't long enough, so I'm going to have to get up and get it. Is in the safety lab, the most important piece of personal protection equipment is the goggles. You have a pair like this in your kit. It's the one ECC or COD, both schools give me. And whenever you're working with chemicals, you should wear this always, even if it's just water, because glassware can break, and you should always have this. I didn't mention last time, it's not a happy memory of mine, but it's an important one. Back when I was a grad student at MSU in another research group, which was literally across the hall from the lab I was in, there was someone I was friendly with, another graduate student. And one of the things in grad school you had to do was certain chemicals, molecules you use for your research, you couldn't buy. You had to make it yourself in organic chemistry. I had to, for one thing, I used a lot, and it was a dangerous reaction. This friend of mine, for something he did, it was a very dangerous reaction. He had done it about 50 times before, so he knew how to do it safely. Well, that day he was in a hurry because he wanted to go to a seminar, and he rushed, and the thing blew up in his face. And I was the first one in the lab to help pull him out, and got him under a shower. The paramedics came, took him to the hospital. I went there with his wife. About 4 hours later, the surgeon came out, and I remember this like it happened yesterday, even though it happened, I want to say 1975 or 70s. That's almost 45 years ago, but it was that indelible event. Surgeon came out, talked to his wife. I was sitting next to her, and she said, he said, your husband's a very lucky person. She said, why? Said, if he hadn't had his safety goggles on, I'd be telling you he was blind now. Luckily, the explosion was so massive that the glass that contained the reaction were just little fragments and hit him in the face around his goggles. He had about 300 stitches. Luckily, they're all 1 or 2 and it all healed, which I was amazed month or couple months later. But I will never forget what that surgeon said. And afterward, I always took eye protection very seriously. Therefore, wear your goggles always. Also in your kit, I didn't bring them up here, you got gloves. If you're dealing with chemicals, anything besides water, I'd put the gloves on too. You have an apron. If you're sloppy, you wear the apron. When we have lab at COD, my students never wear aprons unless they want to, or lab coats, because I show them how to do things safely in the lab, which they do. But still, you should always have eye protection. And at COD, when we have lab in the actual chemistry building, all people, including Dr. White, wear safety goggles, not glasses, goggles, and also wear gloves. And we provide them at the school when you work in the labs there, which we're not doing this semester. All right, let's talk about today's lab. Today's lab, lab number 2, deals with measurements. And you should all see that on your screen right now. Thumbs up, people. Can you see it? Thank you. All right. Now, today's lab, you'll be measuring some things. And Mary Newberg, who's the chairman of the department, wrote part of this lab, and I modified it. Now, she talks about what's accurate, what's precise, what's both accurate and precise. I'll let you read that, how to use a ruler. And today you're going to be learning about measuring things and determining significant figures and how accurate a measurement you can make. And in the first part, you're going to measure the length. And if you don't have a ruler, you can go to this website. I went there to check it out. I have rulers. And Don't click on the part near the bottom where it says printable PDF free download. They're trying to get you to buy something. Just click on the first ruler picture in the upper left-hand corner if you need a ruler. If you don't have a printer, you can just have it on your computer screen and measure it. I think it'll get the job done. And what she wants is take a quarter. If you don't have a quarter, any coin, hopefully you still have a coin around, and measure it. And also something that's square, measure it. Ooh, let's see if I can get it out real quick without making too much of a mess. Yep, here's a piece of plastic. It needs to be dusted. I like because the light comes out from the end. I have some things I made from this. This was leftover scrap that I keep. Now, for one project, when I was working at this one company, we had to adjust the gauge, and the machine shop made for me, and it took them a couple days to get it right. This is exactly 4 inches, 4.00 inches this way. Are you getting the clicking again? I don't know what that is. I tried my cable change. I don't know if I have a bad web camera. Hold on one second. Is it clicking now? Give me a thumbs up if you hear clicking. All right. I don't know if it's my web camera, because it didn't happen during the summer, but I used the HP web camera, now using a Logitech that I got about a month ago. All right. This is 4.000 when it goes this way. Well, there was stuff clicking from falling on my desk. But anyways, this is 4.000 and this is 1.000. It's stainless steel. It's not going to change. Like I said, the machine shop made it for me at one company because I use this to calibrate a gauge. And their stuff was much more exact. Anyways, you're going to measure some things. When you send a lab, all you have to do is send a lab with, if the lab has, like this one, some data and tables you have to put in, send that, and then your answers to the questions. Obviously put a number, which question is what. You don't have to send all the questions. You don't have to, if you don't have a printer, you don't have to write out the whole lab. So like in this lab, and I'm going to show you, let's get back to that. All the pages that have data or questions, or if you want to, if you have a Word document that you're working with, you can just delete everything except the data tables and the questions. But make sure your name's on the top, just in case. So here, no, you don't have to send me. If you can do this as a Word document, you can delete all this, but for the quarter, do the diameter. For your rectangular, do the length, width, and height, or depth. And the volume, in case you don't know, volume is length times width times height. I see another question. Hold on. Okay, I'm glad I helped Ria. All right. Now, the next thing you're going to do is measure volume. Let's talk about volume. Hold on, I got to come over here and get this. This is called a graduated cylinder. You have one in your kit. There are numbers here. It goes from, you don't see 0, it has 10, 20, up to 100. This is measuring milliliters. 1,000 milliliters is 1 liter. I think you've seen 2-liter bottles of pop. Now, so you can see it better. Dr. White has a better one at home because I have my own collection of lab stuff that I've gotten from eBay because I like this. Now, when you put water in here, just like a measuring cup, this will fill up. And I didn't bring water into my office because I got all this electronic gear around other than my tea. And what you'll see is the lines here. Each one of these is 1 milliliter. From, say, 70 to 80, you'll see 10 lines. The one in the middle is 75. You can get 3 significant figures. Now, I'll show you in a second on my drawing tablets, but if you put a liquid in here like water, it's not straight across, it's a U. That's called the meniscus. And you look on here, the bottom of the U. Now, pro tip that I teach in the lab, and I'll teach you, how do you read this better? You put a piece of paper behind it. Now, because of the backlight, you can see it better. But if you're working in a lab like this, a piece of paper or even your hand helps you read it better. So when you're going to read this, put your hand or a piece of paper behind it, and it'll help you read and remember the meniscus. All right, I see a question. All right, we're not doing a test right now. This is a lab. Right before test 1, I'll explain how to do that for test 1. All right, so let's go back to the lab. And she has a shot glass, any kind of container. Start with your graduated cylinder, fill the shot glass or some small container to the top, and carefully pour it into your graduated cylinder. I highly recommend you do this over the sink in case you spill. And pour it in and measure it. Indirect, start with a dry, fill the graduated cylinder to a certain amount, record the volume, pour it into the shot glass, record what's left. Oh, I see what she's doing. Fill it up to 100 or close to 100, record that, then pour it into, hold on. All right, for the labs, all you have to do is put your name on the top where I have name, but it has to be in a PDF file. What I don't want is 4 or 5 individual pictures of your lab from your cell phone. In that file, I also show how you take pictures and make them into a PDF file. They're 2 different ways. If you have any questions, see me after class today. All right, let's get back to this. The second part, indirect, what you'll do is fill it up to, say, right around here, and whatever small thing, you'll pour it till it's to the top, and you'll measure now the new volume, the second one, and the difference between those is the volume in whatever small container you're using. And you'll see, is there a difference filling this up, putting in this, or going this way, which is more accurate? And that's part of today's lab. Remember, because you're doing this at home, that allows you to get credit for 1211 as an actual hands-on lab, which is important. Schools are expecting that. All right. Now, either the indirect or the, for this one, fill it about halfway, record the volume, and put in a couple of pennies or something else and see what happens to the volume, record it again. Now, this is just to give the department and you, how should I say, insurance. Please take a picture of your graduated cylinder and with an object in there. Upload that, and I'll have a separate picture entry lab number 2 in the assignment, upload that picture just as a picture. And that way, if somebody asks me in the future, did you have your students using the lab kit? And I'll say, yeah, look, I have these pictures of them using it. And that's PYA, protect your, and I think you know what the letter A stands for, your back end. And that's for you and me, the PYA. Dr. White plays careful always. All right, and what you'll do is be able to find the volume of those 5 objects by how much the water has gone up. And here's the data you'll put in here, the 2 different ways you were using your shot glass. If you don't have a shot glass, something smaller. And then your objects, pennies or marbles or whatever you have. If you have navy beans, that would also work. And you can fill out these things here. By the way, average volume of 1, if you had 10 objects and the volume of the 10 objects was this, divide this number by 10. All right, the last thing I'd like to talk about, I think that's last, yep, is temperature. In your kit, it'll look like this, covered. I already separated it. Take the top off carefully, and you'll have a thermometer. Now, this is glass. Be careful with it. It breaks. Now, it does have up here, mine does, and hopefully yours does too, this blue thing is to stop it from rolling off a countertop. But sometimes these don't work. If you're going to use this, and between things, if you're going to put it down on your kitchen countertop, take a towel and put it on the towel like this. It's on the countertop, not my hand, and that will stop it from rolling off. Because if this rolls off, it's going to break. These are alcohol thermometers. You can see it's red, not silver, which is mercury. And therefore, it won't be that much of a, it'll be a pain to clean up all the glass. But always, and I do, and if you don't have towels in your kitchen, use a paper towel that you crunch up a little. Now, this is the thermometer. I think you all know how to read this. You do not have to shake it down like a medical thermometer. You just put it in somewhere and wait a little while, and the temperature will rise. Now, I don't know if you can see it. There's a red right here. And you have individual markings, and each one from 20 to 30, there are 10 of them, so each one is 1 degree Celsius. If I say centigrade, that's the term I grew up with, same thing. And you should be able to get 3 significant figures. I just gave you the answer to something. If it's right on the line, call that like 21.0. If it's between 21 and 22, call it 21.5. Now, you're going to be doing a number of things with that. I'm going to follow my own advice. And in your kit, you'll have a beaker, the large one I would use. Glass, they break, so don't drop it on the floor, just like anything else. Also, you'll have in your kit a stirring rod. Do not use the thermometer to stir things. It's tempting, but they usually break when that happens, and you don't want that to happen. Let's go to the lab. Now, I made some modifications from what Mary had, because I don't want you using the alcohol lamp yet, hopefully never. All right. Notice, don't use it as a stirring rod. Hold it. Make sure whatever you're measuring the liquid in, you don't touch the size of the container. Now, what you're going to do is fill a beaker about half full with tap water and measure the temperature. Then add some ice to it. Stir it with the glass stirring rod, let it wait a couple minutes, like about 5, and measure the temperature of the ice water. Now, You can also do salty ice water. Take about 3 to 5 teaspoons of table salt and put it into the beaker with the ice water and use your stirring rod, or you can use your tablespoon too, not the thermometer, mix it. Let it wait a minute or two, measure the temperature. When you're done, that's not hazardous, so you can just dump it down your drain. Now, you can also measure the temperature of boiling water. I'm going to assume you all have access to a kitchen with a stove with a small pot that you can fill up about halfway with water, get it boiling, and then carefully, when you do that, put the pot on your stove and heat it. When it's a full boil, carefully put the thermometer bulb about halfway down the pot. Don't touch the bottom or sides, and record the temperature. And theoretically, at 1 atmosphere, and I'll teach you about the barometric pressure later on, you should have 100 degrees. You may not. One, because of what's the atmospheric pressure now in northern Illinois, Chicagoland. Don't know, I haven't looked it up yet. The other thing is, how accurate is the thermometer they sold us, or they sold you? I got mine free. All right, in the table, temperature of tap water, ice water, salty, boiling water. Once you've done that, let it cool off and you can dump the water down the drain. Be careful, the pot and the water are hot. For this I put in, I changed to better. Here are the questions you have to answer. And if you have any questions about the questions, ask me. And that's today's lab. Now, when you're done with your thermometer, I'd highly recommend you put it back in its case, because you probably need it later in the semester. And be careful, this is a real tight fit. And just slowly, the part with the little rib here is the part that goes on the top of the thermometer. And just go like that and we're done. Remember, wear your safety goggles. And for water, you don't have to wear gloves, but if you like to, I don't think anybody's allergic to water. All right, one more thing I just want to show you real quick. Oh, by the way, I don't know if I mentioned this. My mother was a very good amateur artist. Not one speck of that rubbed off on me. So whenever I do artwork, you are completely permitted to laugh your head off. Just don't fall off your seat and hurt yourself. All right. Here you have a graduated cylinder. Let's assume you have liquid in there and it looks like that. It's going to be a U. Obviously, I'm not an artist, as opposed to flat. You look for the bottom of the U right here, and this is where you measure the volume, not up here. This is called the meniscus. I'll never ask that on a test. But that's how you do it. And that's that picture. As you can see, I'm not going to be an artist. Now, listen carefully. I keep, when I teach, what you do in the lab and what you do on the test separate. The labs are separate. I don't give a lab quiz at the end of the semester or lab final. No, labs are just supposed to be informal. And if you hand in your labs, you should get good grades. Remember, each lab is worth 11 points. Don't forget, hand them in on time. This lab will be due next Thursday. So you have between now and Thursday to do this. It shouldn't take you long to knock this out. If you have any problems, ask me. Any questions on the lab? All right, one of the things I didn't have a chance to do on Tuesday because we weren't here is teach you how to use a calculator, which I'm going to do right now. Now, if you have a different calculator, that's okay. If you can't figure it out, come to my office hour. Hopefully you have a webcam or tell me what type, because there hasn't been a calculator yet I haven't been able to figure out using the manual. And thank goodness, because of the internet, the manuals for every calculator any students ever had problems with is on the internet. All right, this is an experiment. I'm going to not use one, but two webcams. So let's see how this works. Now, because I'm doing this right now, I was going to go through the practice problems for chapter 2. I'll do that on Tuesday, because some of those problems you need to know how to use a calculator. All right, by the way, when I'm moving to the other camera, hopefully you won't get too dizzy while it's moving around. You get to see part of my inner sanctum. That's not what I want. All right, this is the calculator. And I'm going to turn it on. And the first thing, I'm going to clear it. And the question is, are you in scientific notation or not? And right under my finger here, you'll see if I could magnify SCI. And that means scientific notation. Now, if you don't know what it is, for this calculator, blue button, and then right over here on the top, it says SCI and some other things. And now you'll see three things: flow, SCI, and engineering. And you can use your cursor to move it under SCI and hit enter. Now you're in scientific notation. Now, I'm only going to do it once, so I'll do it twice. Hit the blue key, and then above here, it says SCI and engineering, and make sure this is under SCI. Then hit enter. Now you're in scientific notation. How do you do, I'm sorry for the motion on this, how do you do scientific notation? Say you want to do 2.0 times 10 to the 5th times 15. Good question. Well, you put in 2.0. Now, how do you get to scientific notation? You need to do the blue key. I should have done my nails. And then there's a double E above a key, and you hit that. And now you'll see the letter E there. That means E is 10 to the whatever power. And I said 10 to the 5th, so I'll do 5. I'm going to multiply it times 25. Come on, focus. There we go. And I'll hit enter. And you'll see over here, it has 5. Then there's a very tiny times 10, and then much bigger 0.6. And that's how you do scientific notation. Let's do it again. Say I want to do 4.11 times 10 to the 6th. Second key, the double E, which is above a key, I call blue double E. You'll see the E right there. And then 6, 10 to the 6th. I'm going to do it times, I don't know, 3.52. I could do another scientific number the same way. And notice here I get 1.33573 times, then there's a little 10, then there's another number, 0.7, 10 to the 7th. Now, listen carefully, this is important. What if you have to do 10 to the minus 5 or 3? How do you do that? You do not use this key under the multiplication. This key is only for subtraction. What you will use is, you'll see on your keyboard of your calculator a bracket minus bracket. This is the key used for minus 10 to the minus something. So let's clear this. Let's do 5.555, and then I want to do 10 to the minus 3. So I'll do the same thing, blue, double E, but now before I put the number in, I want minus, so I can do this one with a bracket, not this one underneath the multiplication, because that's this for subtraction. And I'll hit this, and I'll put 3. If you look up there, notice E minus 3. E on this calculator means 10 to the whatever power, minus 3. All right, let's do times 66. And you'll see right here, it's 3.663 times 10 to the minus 1. And that would be 3.66 times 10 to the minus 1. So over here, you'll see what power. If there's a little minus sign there, you'll see that it's minus power. If there's no, it's a plus. And that's how you use your calculator. By the way, in case you wonder, there's my desk where I do a lot of my hobby stuff. And there's some of my hobby stuff right there. You got to see Dr. White's inner sanctum. Remember, keep it a secret. And that's how you use a calculator. If you have problem in Chapter 2 problems with your calculator, let me know. Come to my office hours or stay after class, and I've yet to not be able to, sounds like a double negative. I haven't failed to help a student succeed in learning how to use their calculator. By the way, this calculator, which is in my syllabus, let me clear it, shut it off. It's a solar calculator. Don't have to worry about, oh, my battery died. And you can get it at Walmart, Target, and other staples. Walmart, I think, is about $10.50 plus tax. Staples, about the same. Target, I think, is a little higher. But, and for those who you want, you can get it in different colors too. So you need one of these. If you have a bigger one with the fancy graphing, that's okay. And that's how you use a calculator. How are we doing on time? Doing good. All right. Oh, guess what time it is? Oh, I haven't used this all semester. It's time for a new chapter. I love that. By the way, the company that makes this out of Germany no longer does. I've had these for many, many years. I got 3 of them, and I protect them. They don't go out of my house ever. Anyways, it's time for a new chapter. Let's get moving. And that new chapter is matter and energy. And remember, what I'm showing you here is available to you on Blackboard in my lecture file. Now, chemistry is defined as studying matter, how it changes and all sorts of things. And the question is, what's matter? Well, I'm not going to ever ask you this on a test, but you should know it's anything that has mass and occupies space. So I guess you people matter. Oh, that was bad. But anyways, you really do in my heart. And that's matter. And another way of thinking of it is matter refers to amount of mass. Oh, by the way, what is mass? Mass refers to the amount of matter present in a sample or anything, also known, if you're going to stay on this planet, the weight. So anything that has mass and occupies space, we call matter. Now, there are physical states of matter, and there are 3 of them. You're familiar with it, but it's important you know this. The first one is a solid, and you should know the definition. Hint, that solid is something that has definite shape and definite volume. And it says here incompressible, don't worry about that part. But you should know a solid has definite shape and definite volume. And this is a solid, has definite shape, definite volume. By the way, this was made for me in about early 1980s. And the last time I checked it, it was still 4.000, 4.000, and 1.00. It has definite shape, definite volume. This is a solid, stainless steel. Now, the second physical state you should know is a liquid. And a liquid has indefinite shape and definite volume. What do we mean by indefinite shape? Well, if you were to take water and pour it into a glass, it would take the shape of that water. And now if you had a glass, and I don't own any, I once saw it online somewhere, you had a glass that was actually square, not round like we normally see glasses. If you poured the water in there, it would take up the shape and fill that square. Another way of putting it, I can do this. Here I have my water bottle. I have tea and water when I teach. In my home, in the school, I just bring this. And notice it has a certain shape. You can see underneath the label, it's got some ridges, and the water is taking up the shape of this. If I were to pour this into a glass, it would take up the shape of the glass, and that means indefinite shape. But the amount, the volume won't change. Just like in my mug right now, I have approximately, if you can see that, 300 milliliters. It's a lab mug. This I've had for many decades. They make them a little different now, not as pretty as this one. By the way, it's microwavable too. And it's got some good tea in it. So a liquid, you should know, has indefinite shape but definite volume. And the third physical state is a gas. And a gas has indefinite shape. It will fill up whatever container you fill it, because it has indefinite volume. Forget about the compressible. Now, I have here, hint, know this. Let me change that. Dr. White's being subtle today. Hint, know this. You should know what are the 3 states of matter: solid, liquid, gas. If we were in class right now, we'd have class participation. We're not, so you just pretend you're participating with me, and I would ask the class, but I'll do it for you. Class, what are the 3 states of matter? Solid, liquid, gas. I'll say it again. Class, everybody together with me. What are the three states of solid? And this would be really cool because students get freaked out. What's he doing now? And everybody gets into they really do it nice and loud. The first one, solid. The second one, liquid. The third one, gas. You should know a solid has definite shape and definite volume. You should know a liquid has indefinite shape, definite volume, and a gas has indefinite shape and definite volume. If you think about it, if you're in a room and someone comes in with, opens a bottle of, say, perfume, guess what? In a little while, if you're farther away from that person, you'll smell that. Uh, on a worse note, if you're out driving around and some skunk just skunked an animal and you got your window open in your car, you're going to smell it. But that's because gas has indefinite shape and definite volume. And you should know what are the three physical states of matter. And I'd have the class say it again, class participation. So you say it mentally and I'll pick it up. In case you don't know, Dr. White has ESP, also have ESPN on cable. But anyways, first one, solid. Second one, liquid. Third one, gas. So if I ask on a test, what are the three states, physical states of matter? You should know, solid, liquid, and gas. I see a question. Hang in there. Well, we don't deal with plasma in here. We'll just stick to these three right now. But that's a good observation. All right, speaking about good observations, I look at my clock and it's time for Dr. White to do some stretching. I'll see you at 10:55. I'll be right back. All right, ring, ring. Hold on. Let's get started. I have a question for you. Is the clicking still going on now, or is that pretty gone? I wonder if it was something to do with my internet service, because on Monday morning I had a quick loss, and Tuesday they had a major failure. I was wondering if their equipment was failing, and that's why that was the clicking sound. Let me know if you hear it again. Click, 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 click. All right. Thank you for everybody who responded with a good no. I'm glad it's not there. All right, let's get back to work. Again, the three states of matter are, you should know, solid, liquid, gas. You should know solid, definite shape, definite volume. Forget about the incompressible. Don't worry about that. I won't. I should take that out of there. This is what was in the book, but I should remove that. Liquid, indefinite shape, definite volume. Gas, indefinite shape, definite volume. Just like I said, I'm being very subtle. Hint, know this. Hint, know this. Get the message? Didn't know Dr. White could be subtle. All right, now, I'm going to go through some definitions. Most of these I'm not going to ask you to memorize, so I won't put them on a test. By the way, those of you whose last name begins with the letter A through D have everybody else's witness that I said that. Oh, it's on the tape too. But anyways, there's still some words or definitions you should know for certain things that I'll use this whole semester. First one is pure substance. That's a single kind of matter that can't be separated into other kinds of matter by any physical means. It's composed of only one type of atom or molecule, only one substance. So if I were to look at a glass of water, assuming it's pure water, there's only H2O in there. If I put salt or sugar in there, it's no longer pure substance. So I will not ask this on a test, but if I use the term in class, you know what I'm talking about. Quick commercial from Dr. White. Don't forget, everything you see here on the screen is A, in Blackboard, and B, it will be on the video I'll post later today. So you can always go to YouTube for instant replay. Anybody need more time on this slide? I see someone copying it down, so I'll wait. All right. Remember, I have the fastest mouse wheel finger this side of the Mississippi and the other side too. All right, let's move on. Another definition, which I won't ask on a test, but I'll use in this class, is a mixture. A mixture is a physical combination of two or more substances, and I'll teach you what atoms or molecules are later on, in which each substance retains its own chemical identity. That means when you mix two or more things together. Now, on a test, I'm not going to ask you what's a mixture, but I could ask, give an example of a mixture you use in your daily life. And the first one comes to mind is the air you're breathing. That's a mixture of mainly oxygen and nitrogen gas. Another thing is, if you take a glass of water and dissolve sugar in there, it's going to be real sweet, and that's now a mixture. Or you could have taken that same glass of water and stirred in some salt. Now you got salty water, but that's a mixture because the water is still the water and the salt or the sugar is still the sugar. And we call that a mixture. Later on, there's another name you can also use for that. I'll never ask you define what is a mixture. Now, when we talk about substances, there are two types. One is an element. That's a pure substance, excuse me, that cannot be broken down into simpler substances by chemical or physical means. I will never ask on a test what's an element or the next one what's a compound, but I will use those terms in class, so it'd be good that you know what it is. So an element is something that you can't break down into anything simpler by any means, chemical or physical. Now, compound is a pure substance that can be broken down to two or more simpler substances by chemical means. So a compound would be something you can break down. Now, what would be an example of an element? Gold. Gold is an element. You can't break it down to anything simpler. Same thing with silver. By the way, don't forget, you should be learning your periodic table. This is the 37 elements. See, now you know what an element is that I asked you to learn. What would be another element here? Well, let's think. Let's stay in the high rent district. Platinum is an element. And I'll remind myself later to tell you a story about when we get in a certain area about platinum, an unfortunate incident a student of mine had long ago in general chemistry class with platinum. But anyways, platinum is very expensive. I'm not sure how much more if it is than gold or not. Now, what's a compound? Something you can break down into simpler substances. Well, and I'll teach you what this means later on. Water. Water I can break down to hydrogen and oxygen. So the next time you see your friend drinking some water, say, that's a compound? No, don't do that. Friends don't want to hear chemistry when they're drinking, especially water or other things. Nah, bad idea. All right, so element is a pure substance that cannot be broken down to simpler substances by chemical or physical means. You should know examples of that here: gold, platinum. What would be another one? Lead, zinc. Those are all elements. Now, a compound is a pure substance that can be broken down into two or more simpler substances by chemical means. And that would be water. Another one is oxygen gas, O2. That's a compound. Nitrogen gas that you're breathing right now. Bet you didn't realize how much chemistry is all around you. All right, now, another word you should know what it is, but I will never ask on a test, what is a mixture? A mixture is a physical combination of two or more substances, atoms or molecules, in which each substance retains its own chemical identity. Therefore, the air you're breathing is a mixture, and nitrogen and oxygen molecules don't interact with each other. They stay the same, which is a good thing. That keeps us alive, which I hate to say that. I shouldn't say I hate to. I'm glad to say I like being alive. And hopefully you do too. Another way of saying that two or more substances that are present together. The next time you drink tea, that's a mixture. If you have Coca-Cola, 7-Up. By the way, I'm a Dr. Pepper and Werner's person. If you've never had Werner's, you can get it at Jewel. It's a very spicy, highly carbonated ginger ale that I'm addicted to sometimes. It's good. But anyways, those are all mixtures. Oh, here's a good one. The next time you drive by a gas station, the product they're selling, gasoline, is a very complex mixture. Now, when we talk about substances, we need to discuss the concept of properties, which are physical and chemical properties. What's a property? I'll never ask you what's a property on a test, What's a characteristic to distinguish one substance from another? So properties let you distinguish two different things. How can you tell the difference between gold and lead? Which would you rather have, a pound of gold or a pound of lead? Give me the gold. It's worth a lot more money. Well, how do you know you're really getting that? By its physical and chemical properties. Now, what is a physical property? A physical property, one way of saying it, are characteristics of a substance that can be observed without changing the basic identity of that substance. Again, I'll never ask on tests what for you to define physical properties, but you should understand what they are, know one or two. Another way of saying that, there are distinguishing characteristics of a substance used in its identification description. And if we are at COD, I'd invite you to look out the window through the door at the parking lot and say, if you look out there, you can count how many cars are red or blue or yellow or green. That's a physical property of a car. And there are other things. What color shirt or blouse are you wearing? That's a physical property of that. And physical properties are quite important when we talk about elements and mixtures. Now, the other type of property is a chemical property. And a chemical property is a characteristic of a substance that describes the way that substance undergoes or resists change to form a new substance. Another way is a characteristic of a substance displayed only through changing its composition. In other words, how does it react? Now, what are some examples? Well, if you have two cars, one stainless steel, time out for a generation gap thing. How many of you people have seen the movie Back to the Future? Oh, some of you. It's a good movie. And the car they have in there that they make into a time machine, I hope I'm not giving it away for anybody, is called the DeLorean. And one of the most amazing physical properties of a DeLorean is, I think it's the only car, I might be wrong, but I think I'm not, only car that was ever made of stainless steel. And because of that, it wouldn't rust. If you live in Chicagoland, you know all the salt they put down is not good for your car body, because it'll help it rust out. And the fact that stainless steel does not rust is a chemical property of stainless steel. The fact that your car, which is not made of stainless steel, it's made of another type of steel, can rust is also a chemical property. Why do they put paint on top of the metal of your car? To help protect it from the elements so it won't rust, and also makes you want to buy that colored car. And oh, I'm happy I got my colored car. By the way, I always like red cars. That's the only color I've ever had in my life. I was looking at the chat, see if there was any questions to me, and the answer is no. Now, another physical property, or chemical property, I'm sorry. See the stuff in this bottle? Water. Water does not burn. And do not try this at home ever. If you have a fire, how do they put out fires? Put water on that. That's what the fire department does. That's a chemical property of water. Now, do not ever try this at all anywhere. Gasoline, its chemical property, one of them is it's flammable. You don't want it near a match or fire because it will burn more. And that's a chemical property of gasoline. Another chemical property similar, this won't burn, stainless steel, but a chemical property of paper, and do not try this at home or anywhere. I put a match underneath, it's going to burn. And that's a chemical property, indicates how it will change. I'm never going to ask what's a physical or chemical property, but if I ask on test, give an example of a chemical property, you should know. Give an example of a physical property. Now, when we talk about physical and chemical properties, important aspect of that are physical and chemical changes. And a physical change is a process in which a substance changes its physical appearance, but not its chemical composition. Now, the best example is when you go from one state of matter. Ooh, you remember the states of matter? Solid, liquid, gas. Dr. White does brainwashing in my class. And when a substance goes from one state to another, it's undergoing a physical change because it's still water, H2O. So if you have an ice cube and it melts, and you happen to be at a picnic this weekend where it's physical, everybody's doing social distancing and everything, you can point and say, oh, look, there's a physical change. The ice cube is melting. Don't. People are going to give you the weirdest looks. People don't like hearing chemistry at picnics unless you're with other chemists, which you probably won't be. Excuse me. So another one is when you boil water. I'll teach you more about boiling water later in the semester and lecture. And that's when water goes from a liquid to a gas. It's undergoing a physical change. So on a test, if I ask you, give an example of a physical change, those would be one. Now, one I've had students do, if I take a piece of paper and rip it, it's undergone a physical change too, but I like the water one better because it's real chemistry. And I'm a chemist. Now, the other type of change, you talked about chemical property. Well, let's talk about a chemical change. That's the process in which a substance undergoes a change in its chemical composition. And we'll talk about this in terms of chemical reactions later in the chapter or later in this course. So whenever a substance undergoes change to become something new, we call that a chemical change. So unfortunately, if part of your car body is rusting, the metal is undergoing a chemical change. I don't want to scare you, but I will, because I'm Dr. White. Whenever you eat food, and hopefully you do it, my mother taught me when I was about, and told me when I was about 2 years old, remember to chew your food before you swallow or you'll choke. And guess what? I found out she was right. But after you chew it and swallow it, it goes into your stomach. And guess what? You're a walking chemical plant. The food in your stomach is changed to other things and it's broken down. And that food undergoes a chemical change. If you were taking organic chemistry from now later in the semester, I would teach you what those chemical changes are. But excuse me, when you eat food. Now, you keep a secret. Most organic, all the organic chemists I've ever known, including myself, when we were young, we liked to burn things. We were pyromaniacs. Luckily, I didn't burn down my house or anything, my parents' house. But if I take a piece of paper, put a match under that, guess what? It's going to burn, and it undergoes a chemical change. When you light a match, that's undergoing actually a couple of chemical changes. And later in the semester, I'll talk to you that when you light a match, there are actually 3 reactions going on, and that's a lot. And those are all chemical changes. Because if I burn this, this is no longer this molecules of paper called carbohydrates. Yeah, it's a carbohydrate, but it becomes this CO2 and water and some ash. So those are all chemical changes. If I ask on a test, give an example of a chemical change, I'm going to give you 22.5 seconds for you to think of one your own. What would be an example in your daily life of a chemical change? Tick tock, tick tock, tick tock. Clock is ticking. That's a pendulum going back and forth. Oh, it actually should go this way. Remind me, never do that again. Time's up. Let's think of some chemical changes. Now, one that's not too pleasant is, have you ever taken out a bottle of milk from your refrigerator that was in there too long and you smell it? Oh, it's gone bad. It's gone bad. Well, that's because substances in the milk have decomposed or whatever and undergone a chemical change. Now, a nicer one to think of, when you put your foot down on the accelerator, I like that for special effects, and your car goes faster. The gasoline is going into your engine and undergoing a chemical change to produce energy to make your car go quicker. By the way, one day Dr. White would like to have a Lamborghini or Ferrari. I've been in a Lamborghini, but not a Ferrari. I've been in a fast car on the Autobahn going about 160 miles an hour. That was fun too. All right, let's get back to chemistry. So that's a chemical change. And now you know on a test, if I ask, give an example of a chemical change, well, you can say when you digest food. Or, oh, here's one. When you light a candle, the wax is burning in the wick and undergoing a chemical change. But you never thought when you light a candle and watch it burn, you're watching a chemical change. By the way, Dr. White has a nice collection of handmade candles I got in Europe from Gouda, which you call Gouda in the Netherlands. Oh, they're beautiful, big pillars, all hand dipped. All right, switches off. I think I mentioned before, but I'll do it again. If I go click, switches off, this will never be on a test, but there's some things in your book I should talk about briefly. And one of them is conservation of matter, and that is matter is never created or destroyed in a chemical reaction. It's just changed into something else. And that turns out to be something very important later on we'll talk about that helps people like me write procedures to make things you use in your daily life, like your fabric softener, your toothpaste, the plastic of your cell phone. That's all part of it is based on conservation of mass. Again, switches off. We'll briefly talk about energy. It's a component of the universe. It's the capacity to do work. This part is called, if you were a chem major like I was, this is all called thermodynamics. One of the toughest undergraduate courses for chem majors was thermodynamics. We called it thermo. And where I went, IIT, the instructor we had, Dr. Wood, I still remember, old instructor, not that good. And he wrote the book for that course, which was not that good, but I got through it pretty good. Some people didn't. It was really tough. Now, when we talk of energy, there's two types, which is totally off. Kinetic energy, that's motion, energy associated with motion, and potential energy, energy associated with position. I'm zooming through this. Different units are the joule, calorie, like your food, and kilowatt hour, like your electricity. Energy, a calorie is energy needed to raise temperature 1 gram of water, 1 degree C. 1,000 calories equal capital C calorie. And that's how they determine how many calories in most food, by burning it and capturing the heat. And we're going to do a lab this semester. You won't burn anything, but you'll do the calculations. It'll be interesting. If we were at COD, you'd be burning something like, I think at COD they use a piece of bread. At Elgin Community College, I know we use corn chips. Now, when we talk of types of energy, there's also electrical energy, where you look at the flow of electrons, and I'll be teaching you what electrons are either today or next week. And then chemical energy, energy associated with potential chemical changes, which again switches off. But example potential chemical changes would be like the battery you use for your flashlight. That's undergoing a potential chemical change. Click. I've just turned the switch up. It's now full on. You should be taking good notes now. Aren't you glad Dr. White knows you don't know how to read my mind? Now, when we talk about energy, important thing is temperature scale and temperature, which you'll be doing in today's lab when you get a chance to do it, where you use your thermometer. Now, there are different scales, temperature scales. In science, and also in Europe, we use the Celsius. It's abbreviated either by degree C or a little circle and capital letter C. Now, until about 1970s, late 70s, most of us used in the United States the term centigrade. And then it was changed to Celsius. Actually, it was 1948 when it was done by convention, but people didn't do it until really by the 80s, 70s, when the United States, they tried to convince us to go to metric, which didn't work that well. And Celsius is one temperature scale. Now, another scale is called Kelvin. And Kelvin is named after Lord Kelvin, who also has another name before he was knighted and called Lord Kelvin. I can't remember what it is, a great English chemist. And for whatever reason, I never knew why, and I've never taken time to search, they don't call it degrees Kelvin, they just call it Kelvin. Kelvin is used for very, very, very low temperatures and also gases. And we'll learn when we get into gases later in the semester about Kelvin. And being in the United States, the last one, you're familiar with Fahrenheit. If you listen to the weather report this morning, they tell you what the degrees F is, Fahrenheit. That's abbreviated by this. One interesting thing, absolute zero, which is 0 K, Kelvin. This is the temperature when all molecular motion stops. If you go to outer space, you're not at 0 K. I don't know if any scientists have ever been able to get a temperature down to 0 K. They've gotten like a 1/10 or 2/10 of Kelvin above that, but never 0. If that happened, we'd be dead. If it happened. Now, let's look at conversion formulas. And this teaches you how to convert from different scales between each other. Kelvin equals degrees C plus 273. Kelvin equals degrees C plus 273. Fahrenheit equals 1.8 times degrees C plus 32. If I have degrees C and I want to go to Fahrenheit, I put in my degrees C, multiply 1.8, and then add 32 degrees. And finally, if I have Fahrenheit and I want to go to Celsius, I almost said centigrade, degrees F minus 32, and then divide by 1.8 equals this. Now I should change this. And I'll explain why now. You should know how to use these formulas for temperature conversion. It's been almost 2 years now. I had heard some of us were discussing about teaching chemistry. I came to the conclusion, which is more important on my test for general chemistry. Is my mic cutting out? Can everybody hear me? If you can hear me, give me a thumbs up. All right. Everybody's giving me a thumbs up. So Mary, maybe it's your equipment. I can't. Everybody else seems to think it's working all right. Okay, let's continue on. About 2 years ago, give or take a month or two, I came to the conclusion on my test, should I first test how good your memory is, then how well you learned what I'm teaching in chemistry, or should I just teach how well can you apply what I've taught you in chemistry? And I came to the conclusion I'd just rather teach or test how well your ability to apply what I taught you, not what your memory is too. So therefore, in the past, those 3 formulas, students of mine would have to memorize for the test. Good news, you don't have to do that. On test number 1, at the back of the pages, or it'll be a PDF file, I will have an area called Important Information, test number 1. And those 3 formulas will be given to you. So I'm not testing, first of all, how well can you memorize things, but I will be testing how well you can apply what I teach you, which is really learning chemistry. Because anybody can go to the internet and look up those formulas with Google. What's the conversion of this to that? And you can get that formula. So let's look at this. Let's look at the first one. Kelvin equals degrees C plus 273. Since I'm through writing, I'll decode what I just. All right, 3 points. Say sometime in your future, you see this on something I give you. If a gas has a temperature of 101 degrees C, then what is its temperature in Kelvin? All right, starting now, I'm going to train you in something that I highly recommend you do when doing, this is called, everybody take a deep breath, relax, a word problem. Relax. And you'll see what I'm going to do. I'll be doing it throughout this whole semester. This helped me when I was an undergrad and a grad student. And trust me, I took more tests by the time I got my PhD than you have so far in your life, and hard tests. And this has always helped me, and I'm sharing it with you. And I'll be doing that this semester. So what do? You look up here and ask, what are you being asked to find in the units? And I put a question mark and Kelvin. Next, what are you given? The temperature. And then you know, because you'll be given this formula, but you got to know that's the one you need to use. Kelvin equals degrees C plus 273. Now, 273 is an exact number. So it has no role in how many significant figures. This is an addition. So how do we find this? Well, we took the time to figure out that's what we're given. So I can put this in. Add it up. You don't put the K there, I'll never take off a point. And that would be 374. And that's how you do it. Oh, look, Dr. White's going to share the fun. Your turn. Why don't you try this one? If a gas has a temperature of 211 degrees C, then what's the temperature in Kelvin? Have fun. And when you're done, give me a thumbs up. If we were in class, I'd tell everybody, when you're done, look up and smile. And I get people who are smiling in my class. You know, Dr. White always has a happy class, hopefully. Uh-oh, it's terrible humor day. Anybody need more time? Going once, twice? All right, let's do it. Again, when I read a problem, the first thing I do is, what am I being asked to find? What is the temperature in K? And I'll put a question mark and the units or whatever I'm trying to find. Next, I'll look at the problem. What am I given? And the answer is this, 211 degrees C. What do I know? And you can look at important information at the back of test number 1. I also have this on 2, 3, and 4 in the final. Kelvin equals degrees C plus 273. Since I took the time to figure this out, I can put this in. Add it up. I'll do this in my head. And that's your answer. Now, another important thing, let me teach you. And that is on my test. Oh, someone agreed with me. I got it right. Yay. On my test, it pays to show your work. What if you added that wrong? You say you're using a calculator and you push the wrong button. On multiple choice, which I rarely give on my tests, mine are usually short answer or a little longer answer. If you show the work like I just did, but you added it wrong, I'll take off 1 point for math error. If you don't show the work and get it wrong, I give you 0 points, 0. So it always pays to show your work, because that way I can give you partial credit. Now, there's one more thing I want to talk about with this formula, and that's the concept of exact number. Let's assume so if we do another one, the gas has a temperature of 21.5. What is its temperature? I'm abbreviating here because I'm getting lazy. I'm being honest too. In K. So we have this, Kelvin, we're trying to find. The temperature we're given is this. Now, you will be given this formula. I can put this in. Now, this is an exact number because it's part of the definition of this formula. And it plays no role in how many significant figures you get. Now, when you're doing addition, you get the same number of significant figures past the decimal point as the number that has the fewest. This is ignored for significant figures. This has 1, therefore the correct answer is 294.5, because the only number that you use for significant figures is that one. And that's why for addition, it's a little funky. This is 1 past the decimal because that has 1 past the decimal. So remember, in formulas, you should know which numbers are exact numbers. That you'll have to learn on your own. Let's do another one. And here, Fahrenheit equals 1.8 degrees C plus 32. I could even make it 5 points. All right, let's take a look at this. What is the outside temperature in degrees F if it is 14.6 degrees C? So what are we being asked to find? The temperature in Fahrenheit, degrees F. What are we given? The temperature in Celsius. What will you be given? This formula. And that's 1.8 times degrees C plus 32. These are exact numbers. Therefore, how many significant figures here will be the number of significant figures you get in your answer. Also, common mistakes students do is I'll add 32 to this first and then multiply. No, you do this first and then add this. Again, common mistake on test number 1. I'm telling you this so you don't make it. You do the multiplication first, then the addition. So if I do this, 1.8 times 14.6 degrees C plus 32, I'm showing my work. Time to go to my special online calculator, courtesy of Bill Gates, otherwise known as my spreadsheet. One bad thing about being online is it's 14.6. Now my calculator gives me the number 58.28. And therefore, if I come over here to my whiteboard, the calculator gives me 58.28. But this is the number I use for significant figures. How many is that? That's 3 significant figures. So on test 1, 2, 3, 4 in the final, underneath your name, we'll say, please use proper significant figures for all answers. And now you have to round that off, because that's 4 significant figures. And how do we round that off? Keep the 5, keep the 8, keep the 2, use the 8 to round off. That's 5 or higher. So the correct answer for this would be 58.3 degrees Fahrenheit. And that's how you use that formula. I see we're almost time for another break. Remember, I'm going to go quick thing. Through the 80s and good part of the 90s, I spent a lot of time in Europe, mainly Germany, the Netherlands, and some time in Brussels, and also some time in England, but more in Germany and Netherlands. And I'd stay there. Sometimes I'd go for 3 to 4 weeks at a crack, staying in hotels and working at certain research institutes, or for companies I worked at research centers. And I'd turn on the news, my radio, my room, or the TV, and they'd have the weather, and it was always in Celsius. And don't ask me why, even though I work all the time in the lab in Celsius, to know what clothes I have to wear, I'd mentally convert it in my head to Fahrenheit. Say, oh, it's going to be 58 point, I better wear this jacket or this sweater. It's something that has always happened. And that's just a cute little Dr. White story. All right, I think now is a good time to take a break. I'll give you an extra minute, and I'll see you back at 11:50. 11:50, about 5 minutes. I'm going to stretch. We're going to do about another 50 minutes. Hang in there. If you have to leave early, don't forget, I'll be posting this on YouTube. I can go take a stretch break. All right, I'll do it again. Let's get back to work. All right, we were talking about the formulas used to calculate going from one temperature to another. And we just did Fahrenheit, going from Celsius to Fahrenheit. And now what if you have Fahrenheit and you want to go to Celsius? And there you do the Fahrenheit minus 32 divided by 1.8. Common mistake students make with this formula, they divide each of these values, Fahrenheit and 32, by 1.8, and then do the subtraction. Wrong, wrong, triple wrong. Do the subtraction, then do the division. Again, 1.8 and 32 are exact numbers. Therefore, the only number that determines how many significant figures your answer has is this number here. Let's do one. All right, let's take a look at this one, say 4 points. Hint, if your oven is at 351 degrees F, then what is the oven temperature in degrees C? So again, what are we being asked to find? Degrees C. What are we given? 351 degrees F. What do you know? Well, you'll be given this, but you got to know to use it. Degrees C equals degrees F minus 32 divided by 1.8. And we took the time to figure out what is degrees F. So therefore it's 351 degrees F minus 32 divided by 1.8. Remember, do the subtraction, what's in the bracket first. If I go to my calculator, I'll take 351 minus 32. Take that number divided by 1.8. And my calculator gives me a number 177.22222 onto infinity. I don't know about infinity. That's not what I want. Need some help? Everybody see my whiteboard and the problem now? Thank you. So my calculator gives me this answer. And if you were to write that down, I'd take off a point. If it was 4, you'd only get 3. And you'd see on the way I hand back the points for, and I'll talk about this right before test 1, you'd see SF, significant figure. That meant an error, and I took off a point. So what do you do to get this right? Well, look at this. How many significant figures? 3. How do I round this off to 3 significant figures? Keep the 1, keep the 7, keep the 7. I use this to round off. Is that 4 or less, or 5 or greater? And time's up. It's 4 or less past the decimal. I'll drop that. And the correct answer for this problem is 177 degrees C. Now, since we're running a little, I missed Tuesday, I'm only going to do one of these problems now, but we'll do more because they're in the practice problems for this chapter on Blackboard, and I hope you're doing those. Now, time to talk about something important. Some instructors, after teaching this, go like this. Well, if the temperature is degrees F, say 175 degrees F, what's the temperature in Kelvin? Guess what? I have never, ever had to do that. It's just trying to trick you, knowing you have to first go to C, then put this in there. I don't trick people on tests. Therefore, the examples I just gave you are the only ones. I'm not going to ever ask you to go from Fahrenheit to Kelvin or Kelvin to Fahrenheit. I've never done it, and I've been doing this a few more months than you have. A lot more months, a lot more years. Keep my mouth shut. And that's temperature. And we'll do some more when we go through the practice problems for this chapter. All right. Click. Will this be on a test? Switches off. But we're going to do a lab on this. I'd like to cover this briefly now. And there's something called heat capacity. All substances have what's called a measured specific heat. And the heat can be calculated by this formula. Q is heat, mass times the specific heat times delta here means difference in temperature. Now, here I have it in joules. You could also have it in calories. Mass is one way in chemistry is grams, and delta T is the temperature difference. It turns out this is an important thing in our daily life. What? What do you mean, Dr. White? How many of you have ever picked up something like a bag of potato chips? You know, the dangerous stuff. By the way, one of the most dangerous places in the supermarket for me is the potato chip aisle. I try to walk as far away from that. My favorite are the Lay's sour cream and onion potato chip. And also I like the Doritos. Never mind. But if you look on the package, unfortunately, I see a lot of people give me thumbs up. You'll see the calories for a small amount. You never eat that much. You always eat more. At least I do. Sort of like Jay's potato chips. You can't stop eating it, even though Lay's is better than Jay's. But that's my personal opinion. But you see how many calories. How do they do that? By doing an experiment, which we're going to do one. Actually, we won't do it in your lab home, but we'll do it on paper. I'll give you a lab, and the data has already been collected, but you got to know how to process it. Where you burn something and you capture the heat in the water by the flame it produces. It's pretty amazing, and I have a YouTube video of that. And you measure that temperature difference, you know the mass that burned, and you can find out how many calories something has. And that's how they find out how many calories something has. And unfortunately, all the good things in life seem to have a lot of calories for a small amount. You know, like potato chips, onion rings, they're right. But anyways, that's that. Oh no, guess what time it is? It's time for a new chapter. We just blasted right through that. And don't forget, what are the three physical states of matter? Everybody say it silently. I'll say it out loud. Solid, liquid, gas. And you should know that and what their definition about volume and shape. I won't go through that now. So let me open up a new chapter. That's not what I want to do. Does everybody see chapter 4 on their screen now? Give me a thumbs up. Thank you, whoever said that. All right, chapter 4, atoms and elements. Yay, we're finally really starting to get into chemistry, the good part. Dr. White's happy. So, what is an atom? Click the switch. Is this on a test? Is on the on position. You should know an atom. An atom is the smallest particle of an element that retains the characteristics, all of the characteristics, both physical and chemical, of that element. I'll never ask on a test, but I thought it'd be neat to know. I thought it was neat when I found out, where does the word atom come from? Well, it comes from the Greek word, and I'll probably butcher this, atomos, which means indivisible. I butchered that one too. But anyways, atom, you should know that's the smallest particle of an element that retains the characteristics of that element. So if I ask on a test, 3 points, what's an atom? Well, here it is. The smallest particle of an element that retains the characteristics of an element. Remember, everything you see here is on Blackboard for you to download 24/7, assuming you have internet connection and the school's up and running, which most of the time it is. It did go down once a couple of years ago, but that's rare. Just like I lost it on Tuesday. Ouch, that was rare and hope it doesn't happen again. Atom. Now, if you look at my class ring here from IIT, can you see the here? No, don't look. But it's made of real gold. This is back when they made good class rings. And this is made up of atoms of gold. And that's all the atoms come together to make what you see my ring. But atoms of gold, if I take one atom of gold off here, I can't do that, but if I could, it would have all the characteristics of the gold you see in my ring. And same thing for other things like silver, copper, other elements, atoms. Dr. White loves atoms, so does Mother Nature. But then again, I'm a chemist. Back about the late 1700s, 1800, and for this, in the next slide, I'm going to say click, the switch is off. There's a great English chemist, Dalton, in 1808, and he came up with the first atomic theory. There are things going around that are just out and out crazy, like you have to have all this mysterious stuff and vapors and gases and wind, earth, and fire was all, no. Dalton came up with, first of all, every element is made up of tiny particles called atoms. Again, switches off for this, but this was an important foundation upon which all chemistry was built. atoms of a given element are identical to one another, different from other elements. So if I have gold, its atoms, whether I get gold from a mine in the western part of the United States or another part of the world, it's going to be the same atoms. But if I have atoms of gold, it's going to be different from atoms of, say, lead or silver. And that's because you're talking about different elements. Dalton also came up with the concept atoms of two or more different elements combine to form compounds. Again, switches off. And a particular compound is always made up of the same kind of atoms and the same number of atoms. Therefore, we think about water compound, and I'll teach you about this later on, that always is made up of two hydrogens and one oxygen, H2O. Water is always H2O. If I go to the planet Venus or Mars and I find water, it's going to be H2O. If I, here in Chicagoland, analyze the water, it better be H2O. It is. If I go to one of my favorite cities in the world, which I haven't been to in too long of a time, Amsterdam, water there is H2O. By the way, quick little thing. I spent a lot of time in the Netherlands and Amsterdam too. I came up with the saying, you know what it means if you're not having a good time in Amsterdam? You're dead. Amsterdam is a wild city. So is Guadalajara. Now, another one, same thing, would be salt, table salt. And I'll teach you later on, but I'll show you now. Table salt, that's awful. Let's try this one again. Table salt is made up of sodium and chlorine. Sodium chloride, this is table salt. You know, stuff you put on your French fries. When you cook, you add to your different dishes. Or just regular salt. By the way, I'll teach you why kosher salt is better than table salt when you're cooking later on. And this is table salt. And if you get salt here in the United States, it's NaCl. If you go to, pick your favorite country in the world, India, NaCl. China, NaCl. Brazil, NaCl. Oh, by the way, if you ever go out to breakfast, lunch, or dinner with a bunch of chemists, and I've been guilty of this many, many times, one of us will say, can you please pass the knuckle? Knuckle? True story. I do it all the time. I'm a chemist. What do you expect? Now, again, Dalton came up with the concept atoms of two or more different elements combined to form compounds. And a particular compound is always made up, that should be O, not PF, of, I've been hit by the dreaded wrong spelling virus. Not really, didn't catch it. But anyways, of the same kind of atoms and the same number. And a very important concept, the next one, again, this won't be on a test, a chemical reaction involves rearrangement, separation, or combination of atoms. This is one of the most important concepts he came up with. Atoms are never created or destroyed during a chemical reaction. They're just shuffled differently and put together differently. So whenever you do a chemical reaction, you don't destroy the atoms, they're just combined differently to make new compounds. Now, about 100 years later, before I get into that, switches on. If I had a dial, you know, like a volume, and you could only turn it up to 10, I've just turned it up to 15 or 20. By the way, that's a ripoff from the cult movie Spinal Tap. Weird, strange movie. You should watch it. Let's talk about, now Dr. White's getting really fired up, the parts of an atom. And we call those subatomic particles. And what does the word subatomic mean? Sub means under. How many of you ever heard the term submarine? Sub means under, marine, sea or water. And that's a boat that goes under the water. Good news. I'm not going to start singing Yellow Submarine by the Beatles. You know, we all lit and I said I wouldn't sing it. But anyways, submarine goes under the water, a boat. What's subatomic particles? Those are very small particles that are the building blocks from which atoms are made. They're particles that are smaller, under atoms, subatomic particles. All right, this is probably one of the most important things I'll teach you this semester. What are the subatomic particles? Hold on. When I was taking notes as an undergrad, if something was really important, I'd put some stars. If it was like, you better know it, I put the stars in the word IMP. You should too. All right, the first subatomic particle are the electrons or an electron. You should know that an electron has a negative charge. First subatomic particle is the electron. And electrons have a negative charge. The next subatomic particle are the protons. And a proton has a positive charge. Electrons, negative charge. Protons, positive charge. And the third and final, ooh, I'm getting all choked up over this, so important. Third and final one are the neutrons. And the neutrons are subatomic particles that have no charge. So you have the electrons, protons, neutrons. If we're in class right now, I'd say, everybody, it's class participation. And some of you just go, electrons, protons, neutrons. I said, come on, with some feeling, it's the beginning of the semester, louder. And then the whole class would go, electrons, protons, neutrons. Thank you, class. And I do it again because I'm going to make you remember this. What are the three subatomic particles? Everybody together. Electrons, protons, neutrons. Thank you. Remember, electrons have a negative charge. Protons have a positive charge. Neutrons have a negative charge. How many of you have ever heard of the cartoon character Jimmy Neutron? If they had asked me, I wouldn't have called him Jimmy Neutron. I call him Jimmy Electron, because that's, you'll learn later on, where all the fun is in chemistry. Not the protons, they're important, but no, it's the electron. But nobody asked me, and they didn't call him Jimmy Electron, even though that would have been much cooler. All right, think about it. Every element in the periodic table, every element in our life are made up of only these three building blocks: electrons, protons, and neutrons. And how many determine which element it is. And we'll talk more about that. So let's do it one more time. Repetition is good for your grade. See, Dr. White knows how to get your attention quick. All right, what are the three subatomic particles? First one, everybody, electrons. Second one, everybody, protons. Third one, everybody, neutrons. Electrons have a negative charge, and you should know that. Protons have a plus charge. Neutrons have no charge, which is why I wouldn't have called Jimmy Neutron Jimmy Neutron. Now, switch is still on. Back about the early 1900s, 1905, 1910, give or take a year or two. That's only 100 years ago in the history of mankind. That ain't that long ago. When we looked at the molecule, the atom, and started trying to understand the subatomic particles, the electron, proton, neutron. I slipped that in again. Sneaky, aren't I? There are some very important experiments done by great chemists. The first one I'd like to talk about is Thompson's cathode ray tube. Now, how many of you, and now I'm going to show my age and do a generation gap, how many of you have seen the old tube television sets? You know, not the LED ones. That tube is actually called a cathode ray tube. They don't call it that, they just say it's a TV or tube TV. Well, cathode ray, what you're actually doing is shooting electrons onto a screen, and they fluoresce to give you the image. It's a little different with what we have now, like your monitor, where you're seeing Dr. White. That's other chemistry, which I won't go into this semester. I'd like to, but I won't. And here, I shouldn't. If we look at Thompson's, he had electrons were arrayed. That's what's hitting the screen. And he was able to find out that electrons, which are the rays that make the screen light up, have a negative charge. So you should know, again, that Thompson's cathode ray experiments determined that electrons have a negative charge. If I were to ask you, what's the significance of Thompson's cathode ray tube experiments, you should be able to say it determined that electrons have a negative charge, which was a great discovery then. Now, another great discovery was done by, both these were English chemists, I think, were Rutherford's gold foil experiment. And Rutherford's gold foil experiment dealt with the nucleus of the atom. Now, I'll be teaching you again, but the nucleus, and I'll go through this again, is the center of the atom. Remember, the atom is the smallest particle of an element that has all the properties of an element. And Rutherford did some gold foil experiments. And let me talk to you about it. Let's hold on one second. Let me see if I can jump out. Ooh, this is a nice one. All right, hopefully you can all see what's on the internet. Can everybody see this little like semicircle here, or this one where a little beam is coming through? Can you not? Now can you see it? Good, thank you. Zoom sometimes gets strange. All right, Rutherford's gold foil experiment. In this box, you had a way of doing very high energy particles. And you had very thin gold foil. Thin like, how many of you have ever seen gold leaf? That thin. Or if you're not familiar with that, you know how thin a piece of tissue paper or better yet, onion skin. If you've ever seen onion skin, that's pretty thin. And what they did was shoot these high energy particles, and around it was this detection screen that would light up, fluoresce, like a little spot, wherever those particles were deflected. Now, let me teach you something about doing research in academics. And come on. If you ever get your PhD, see you later, Melissa. Remember, everything will be on YouTube. If you ever are getting your PhD, like Dr. White did, you join a research group, and you join a group you want to do research in. I did. And the professor I worked for, Dr. Roosh, I'll forever be grateful for the foundation of organic chemistry he helped build in me. And I did too, but really working under him. You get a research project and you work on trying to solve some problem, and you do experiments. Some of them he tells you what to do, and some you do yourself. And eventually you solve that problem, and then you write it up and get your PhD. Well, anyways, if you do an experiment, you get results that are totally unexpected, your advisor will say, why don't you do it again? And you get the same results and say, why don't you do it another time? And you still get the squared results. And you'll come out and say, I'm going to watch you do it. Well, I can see Rutherford having a graduate student doing this experiment. And the amazing thing was that when they had these high energy particles coming at them, some of them bounced right back from the gold foil. Let me show you that picture again. See right here how some of these were bouncing back right here, the red lines. That's like shooting a cannonball at a piece of tissue paper and having it bounce back at you. Whoa, what's happening? And I can just see Rutherford telling the grad student, why don't you do it again? Really? Do it again. Hold on, I got to come out and watch you do it. It really happened. And that was just unbelievable that it happened. And what Rutherford was able to deduce, come up with, I use fancy words sometimes, for that gold foil experiment was that the nucleus was very dense. It was so dense, this tiny little center of an atom was so dense that it would block these particles and either shoot them to the side or make them bounce right back. And he found out that the other thing you should know is the nucleus contains protons and neutrons. So you should know Dr. White's going to be subtle. Everybody get the hint? You should know Rutherford's gold foil experiments help determine that the nucleus is dense and contains protons and neutrons. And the electrons are outside the nucleus, and I'll teach you about that in another chapter. But from Rutherford's gold foil experiments, you should know that the nucleus contains protons and neutrons. And this is extremely important. Now, question would be, how dense is that nucleus? And let me give you an example. First of all, I'll give you time for you to write that down. because this is one of the most, this is really important. Hint, you should know this. All right, here's an example. If I had an atom and the nucleus was the size of a softball or a grapefruit, this is the nucleus. It's very dense. The electrons are filling what we call the electron cloud that goes 1.5 miles that way and 1.5 miles that way. The nucleus is only this big. The whole atom is 3 miles in diameter, but the nucleus with all the protons and neutrons are only this big. It's super, super, super dense. And Rutherford was the one, ooh, fancy word time, elucidated that. Fancy word, elucidated, means he figured it out. Dr. White knows some 50-cent words, fancy words. Now, when we talk about elements, they have something which we call the atomic number. And the switch is now on to 30. If it only goes to 10, I've cranked it up to 30. You should know this. And the atomic number is the number of protons in this nucleus. By definition, the atomic number is the number of protons in the nucleus. Now, something I'm going to teach you right now. All atoms have a net zero charge. Well, if a proton is a plus charge, an electron is a negative charge, if you have so many protons in an atom, which is determined by its atomic number, then the atomic number by definition equals the number of protons. But because of this, all atoms have a net zero charge. That also tells you how many electrons. So if I know the atomic number of an element, I also know how many protons are in that element, that atom of that element, and I also know how many electrons. Why? Because all atoms have a net zero charge. Therefore, the atomic number tells me how many protons and how many electrons. Hang in there while I find something that I should have had open before. All right, I'm going to ask thumbs up, people. Do you see the periodic table on your screen right now in green? Zoom tells me you should be seeing it, and this is how should I say, bug in Zoom. Let's try it. Now, can you see it? Thank you. All right, this is a periodic table. We'll talk more about it during the semester. But the number in this case, this periodic table in the upper right-hand corner is the atomic number. And this is the periodic table I will allow you to use during all the tests. Notice it doesn't have the names on there. You've got to learn that. But if we look at how many protons, how many electrons in carbon, carbon has this element is symbol C. The atomic number is 6. Therefore, it has 6 electrons, 6 protons. The atomic number right here tells you how many electrons and protons in that atom of that element. If I asked you how many protons and electrons are in bromine, well, you have to know bromine's chemical symbol is Br, and here in the upper right-hand corner, 35. So you now know bromine has 35 electrons, 35 protons. I will never ask you to memorize those numbers because you're going to have it on your periodic table. The ones I use all the time, I know by heart by now, but once in a while, Dr. White still has to. Like if I asked you, how many electrons and protons are in gold? Ooh, let's find out. Well, you have to know Au is gold, and the atomic number is 79. The atomic number tells you how many protons, how many electrons, and therefore there's 79 protons and 79 electrons. I'm going to let you find one. Sodium. How many electrons, how many protons in sodium? Your turn. I'm going to let you have some fun. All right, time's up. Let's see someone. And the answer was given as correct. Let's take a look. Sodium, you should know, is Na. The atomic number for sodium is 11. That means it has 11 electrons, 11 protons. Remember, atomic number tells you how many electrons and protons are in an atom of that element. Now, I think you've all heard you need calcium for strong bones and strong teeth. Therefore, how many electrons and protons are in calcium? Your turn. See, Dr. White shares the fun. And let everybody have time to figure it out. See, chemistry is not that hard. All right, let's look at it. Calcium, you should know. If not, this weekend, practice the chemical symbols. Write them down and say them 5 times. And you can use this periodic table, or you can just go online and look at it. There are millions of periodic tables online. And here, calcium, you should know, is Ca, and the atomic number is 20. Therefore, calcium, the element, has 20 electrons, 20 protons. Oh, let's look at another one. I'll let you try. How many electrons and protons are in oxygen? And if we look at oxygen, it has 8 electrons and 8 protons because the chemical symbol for oxygen is O. I'm going to do one more because I like to do the following. You'll hear me in a second. Krypton. How many electrons and protons are in krypton? This is the last one. I see somebody's already got it. Time's up. Krypton is Kr. By the way, in our universe, unless I was kidnapped to another alternative universe, krypton at room temperature is a colorless gas. It's not a green solid that kills Superman. Anyways, krypton, Kr. How many electrons and protons? Look at the atomic number, 36. That tells you there are 36 protons, 36 electrons. And that's krypton. By the way, if you use flashcards, that helps you, use them. For me personally, I like writing them down, saying them a couple of times. Whatever way that's legal for you to memorize it, do it. So you should remember atomic number. That's the number, by definition, it's the number of protons in a nucleus. However, all atoms have a net zero charge. Therefore, atomic number also equals the number of protons, because the electrons are canceled out, or protons are canceled out by the charge of the electrons, plus and minus add together to get zero. And that's always true. By the way, if you find an exception to that, let me know and we'll be rich beyond my wildest dreams. My wildest dreams when it comes to large sums of money goes beyond my own Lamborghini Countach fighter jets, which I'd like to play with, my own Pacific Island. Beyond that, trust me, what I'm telling you is it doesn't exist. If I look at the clock, we've had a long day. Thank you for sticking around. Before I let you go, everybody have a very happy and healthy Labor Day weekend. I hope you have a good time. Sunday, I'll be at are you ready for this? A Zoom picnic with some of my friends. We get together in front of our webcams, and it's a BYOB, BYOF, and BYOWC. Bring your own booze, bring your own food, and bring your own web camera. And with that, I'm going to say, Gang gesund. I'll see you on Tuesday. Don't forget the lab is due today. By the end of the day, I think I've got this set up for like 8 or 10 o'clock tonight. You should get it in before you get any penalty points. It's simple, upload it. Don't forget to upload the home agreement, whatever that's called. You can do that with lab number 1. It works. I checked for those of you who did it already. And don't forget, by next Tuesday, hopefully you've uploaded the new signature agreement. With that, have a healthy, safe time. Gang gesund. I'm done. Hold on. Bye. Gang gesund. Have a great day and a great weekend. I'll see you on Tuesday. And don't forget to be safe when you do your lab.